Hello, and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. As everyone knows, really the underpinning technology in terms of, the acceleration of electrification in the automotive space and in all kinds of different sectors has to be battery technology. And we talk about batteries quite a lot on the show. We've had people on from different companies with different technologies and different manufacturing processes, etc. So there's a lot of battery content on the Avid podcasts. And for today's episode, we've got something a little bit different. So a different kind of battery technology. And we've got Jerry Barker, who is the Chief Technology Officer at Faradion. And he is here to talk to us about what they're doing with sodium ion based batteries. So welcome to the show, Jerry.
Hi there. Hi, Ryan.
Hi.
Good to be here.
So if we could start off, Jerry, just by kind of setting the scene and getting to know a little bit more about you and your background, that would be great. So tell us about you.
Okay, thanks, Ryan. Yeah, so as Ryan says, right, I'm CTO and founder at Faradion. I've been in the industry quite a few years, more than 30 years, I'm guessing. So I did my degree, my undergraduate degree in chemistry at Brunel University in London, and I wasn't too bothered about battery technology right back then.
Yeah.
But, it was all kind of primary cells and Duracells, Energizer, that kind of stuff. There wasn't that much interest in battery technology, right?
Yeah.
If you spoke to someone in the street, Ryan, about batteries, they assumed it was, it was alkaline manganese or something, right? There was no real interest.
Yeah.
But I got an interest during my undergraduate degree in like advanced materials, applied advanced materials. So I decided at that stage that I was going to do a PhD and looked around and ended up going to Exeter University to work with a guy called Professor Bob Slade. In fact, I was his first PhD student at Exeter University, which is down obviously in the southwest of England.
Yep.
And as I say, I was his first PhD student. And what we decided to work on was, strangely enough, solid electrolytes and electrode materials for lithium batteries. That was where his interest was lying.
Wow.
And I kind of thought that, I saw it as a good fit, right? I wasn't interested in doing basic research or research just for research purposes. I wanted to do something a bit more applied. And so Bob convinced me over, a kind of long period. I went down and talked to him a couple of times, and he convinced me that this was something that was moving quite quickly, right? That maybe there was mileage in battery technology and also fuel cell technology.
Yeah.
So this is now going back to the late 1970s. I went down to Exeter University to do the PhD, and I guess it's all been downhill since then, right? So I spent 3 good years at Exeter, looking at, strange enough, at that stage, going back all the way into the late 70s, early 80s, the kind of pinnacle of battery technology, of research in battery technology was lithium metal technology, right?
Okay.
This is stuff that Stan Whittingham was working on at Exxon. So Stan now has just got the Nobel Prize, right? Shared the Nobel Prize.
Yeah.
But Stan Whittingham at that stage was working on, high energy density lithium batteries. And if you remember way back when, if you know your history of lithium batteries, he was looking at lithium metal anode with things like titanium disulfide as the cathode, as the depolarizer.
Yeah. And
suddenly you've now got rechargeable batteries based on lithium metal anode and these chalcogenide cathode materials. And suddenly, instead of being something that is only a primary cell, you had secondary batteries that looked commercially very promising.
Yeah.
So that's what we were currently, we looked at some other materials, so the Exxon guys were looking at things like TiS2, and had published and patented these things and were trying to commercialize. and we were working on things like lithium V2O5 and lithium niobium oxide, so new materials as depolarizers in the cell.
Okay.
So that was where it kind of got me started on the lithium batteries work.
Wow. Yeah, right at the cutting edge of the dawn of the lithium era.
It was very easy, Ryan, then, right, to keep up with what was going on in the literature, because you could name everybody, right? There was maybe 50 people in the whole world working on.
Yeah, I was gonna say you probably could fit you all in one room.
Yeah, we knew everyone, right? You could read the papers, the articles coming out in journals, and you could basically keep up to date very easily with what the big advances were.
Yeah.
Totally different now.
What was so back then? What was the driver? So what kind of applications were people thinking about with lithium in mind? Did you guys have any idea back then of where it would lead to?
Yeah, we did. Obviously, primary cells, we kind of knew then that wasn't really a long-term sustainable future, right? And just having primary cells, you use them, you throw them away. So yeah, for kind of consumer goods, I think one of the biggest applications initially that Exxon were interested in was telecoms backup.
Okay.
So backup, stationary backup. There was no idea about electric vehicle applications until maybe 20 years later.
Right. You weren't kind of eyeing up the milk floats going down the street, thinking, "Wow, we could make that better."
Hey, we had the biggest deployment in the UK of electric vehicles at that stage, right? I think there was 100,000 milk floats on the road. So we were the biggest EV. We were the early adopters in the UK. We lose sight of that, right? It was all lead acid technology, but we did have a large deployment of electric vehicles, albeit they're only going at about 5 miles an hour.
Yeah, they probably did more harm than good, I think, in the early days.
Probably.
Trying to get over those. Get over that. So then, kind of winding the clock forwards a little bit, you did your PhD, and then what happened? Where did you go next?
Yeah, no, I straight out of university. You're typical when you come out of university at that stage. You apply to all the big companies for a job, right? So I actually got a job at British Petroleum.
Yeah.
So that was up in London. So I moved to British Petroleum directly after my PhD, and was working on conducting polymers. And conducting polymers are materials that have potentially lots of applications. They're used in things like OLED devices now, actually. But at that stage, one of the proposed applications was batteries. So I then went to British Petroleum and headed up their research into lithium, strangely enough, lithium and also sodium batteries based on conducting polymers. So again, there was still lithium metal or sodium metal anode with a conducting polymer as the cathode, as the kind of depolarizer.
Yeah.
So that was pretty good, actually. I had the opportunity when I first got to BP. BP were great, right? I loved it at Sunbury. It's just like basically working on university research campus. It was absolutely fantastic. A lot of very smart people there.
Yeah. And
within getting to BP at Sunbury, within 6 months, they asked me whether I'd like to spend a bit of time at the University of California, Santa Barbara. And strangely enough, I said, yeah, that would be okay. Okay. So if you really somewhere, then I guess Santa Barbara wouldn't be a bad place to go.
Yeah, Sunbury. Sunbury's not bad. Sunbury on Thames.
West London to the West Coast. I guess it was a pretty good deal.
Yeah.
But I went to Santa Barbara for a while and worked with. Wasn't at the time, but now is another Nobel Prize winner in chemistry, Alan Heeger. And we worked on sodium batteries, basically. Sodium batteries using conducting polymers. So it's kind of strange, really, how these things happen. And then came back to the UK, and then BP kind of lost interest. At that stage, BP decided that it didn't want it. It wanted to really focus on core activities as a company.
Yeah.
So I transferred to BP Solar, who at that stage were one of the largest photovoltaics companies in the world. Two of the big ones at the time were BP and Shell.
Right.
It's funny how right? Because they're now back into it again.
Yeah.
I joined BP Solar and I headed up BP Solar's, by training at that stage, I was an electrochemist now, right?
Yeah.
Having worked so much in batteries, I was a pretty good trained electrochemist. So I headed up their work on electrodeposition of semiconductors, 2,6 semiconductors for photovoltaic applications.
Right.
And we eventually took that to pilot production in California. That transferred to California as well. And that was an interesting technology. It really was. We, as I say, we scaled it up to it was a multi-plate electrodeposition process where we were making high purity semiconductors from an aqueous deposition method, electrodeposition method, which at that stage was kind of unheard of.
Yeah.
So we were making meter square size PV devices by electrodeposition. So I kind of love that actually, but but again, things move on, right? Things move on.
Yeah.
You know, I kind of guess my first love was still batteries. So even though I was still working as a kind of bench electrochemist, I guess, as my favorite thing is actually doing the science, I decided I really wanted to move back into battery technology. And strangely enough, you know, rechargeable batteries had moved on a bit at this stage. So I joined a company called Valence Technology, kind of well known in the lithium ion area.
It
has a very interesting history.
Yeah.
And Valence Technology at that stage had two facilities. You know, I won't go into all the background to why they had two facilities, but they did. It's a lot to do with, you know, buying up the relevant technology. Their headquarters was in San Jose, California, but they had a satellite R&D facility in Denmark.
Right.
So I moved to Denmark for a while, and with the idea that I was moving to Denmark permanently, right? So I moved to Denmark, and then within 6 months, they decided that a 9-hour time difference with San Jose just wasn't working very well. So they invited a few of us to transfer to San Jose. So I moved. So I didn't even unpack, basically. I packed everything to go to Denmark, and then I never really unpacked anything. We just transferred everything, my wife and I, and we transferred to San Jose, which wasn't, again, a difficult problem. Right?
A little bit sunnier than, no, not casting any kind of aspersions about Denmark's weather or anything like that, but San Jose is a little bit sunnier than Denmark.
It was a bit warmer. You know, I liked it in Denmark, actually. It would have been nice to stay there a bit longer, but, you know, we transferred to California again. Obviously, I knew California quite well, so we moved to San Jose, and that was the headquarters for Valence Technology. And at that stage, we were working on a lithium metal V6013 rechargeable battery with a polymer electrolyte, and in a lot of ways it was good technology, but we hadn't solved, or not that anyone had solved, the problem with reversibility of the lithium metal anode. So dendritic lithium, mossy lithium, high surface area lithium meant that even though a lot of the performance characteristics of the cells was good, the safety aspects were not good.
Yeah.
Right? High surface area lithium, you know, a liquid fraction of electrolyte, even in the polymer, right? It's a gelled system. It's not a dry polymer system. It's the electrolyte, means that when you get into safety abuse conditions, there can be a problem. And that's really what put paid to the technology, this lithium V6013 battery.
Right.
So we worked on that. And this was we're now talking kind of mid 1990s. And lo and behold, Lithium Ion had just kind of come up, right, from Sony. Sony started in, as you know, everyone knows, 1991. With their hard carbon lithium cobalt oxide system that is migrated into graphite lithium cobalt oxide.
Yeah.
And clearly that had a completely different safety performance than using lithium metal anode cells. So Valence at that time decided it would transfer to being a lithium ion company. Came away from lithium metal, even though I had a few contracts and we sold a few batteries, right? We did sell a few of these things. We had contracts with Motorola for cell phones and all kinds of good things. But as soon as you got these things to a decent size, and by the way, at that point, we were working in collaboration with General Motors. to make an electric vehicle battery out of lithium V6013. But General Motors didn't like the safety characteristics too much.
Yeah. So,
So
and that just because there's probably a little bit of a nuance there that people might not have picked up on. So you've talked about two different kinds of lithium battery technology: the lithium metal and lithium ion. So just like really kind of high level, what's the difference between the two?
yeah, really good point. It's the crucial difference, right? So in a lithium metal system, when you're constructing the cell, you have a film, a foil of lithium metal, and generally in a commercial cell, that lithium metal anode would be something like 75 to 100 microns thick. It's not insignificant, right? This is reasonably thick in electrode terms, and that would match up with the whatever a cathode material you're using. In our instance, it was V6013. That's actually a massive excess of lithium over what you need for the reaction. When you charge and discharge that lithium electrode, so that's what you're doing when you're doing the discharging and the charging of the cell, you get high surface area lithium formed.
Yeah.
In any kind of abuse condition, a short circuit, a crush, in some kind of hot condition, perhaps, that really is a potential safety hazard. It's the nature of this high surface area mossy lithium in combination with a volatile electrolyte.
That's a nice way. So the high surface area bit, what you're talking about there is on the lithium sheet, you get a growth of
growth. You do exactly.
And it looks a
right.
bit like moss.
It does. Mossy lithium is quite
Mossy
often
lithium.
called, right?
Yeah.
Search it on Google, you'll see lots of it. It goes mossy. The best thing that happens is it goes mossy. It also goes dendritic. When it goes dendritic, it can penetrate through your electrolyte and cause an internal short.
Yeah.
Which is another problem.
Yeah.
So the migration was to lithium ion, right? So people had learned a lot about putting these cells together, but didn't really want to be using a lithium metal anode. So the migration meant that we turned to a carbon anode material, and that initially started out being either a soft carbon or a hard carbon, but soon changed to a graphite.
Yeah.
And when you do that, there are some implications that have come about, right? If you do that, all the lithium that's in the cell really has to come from the cathode material. So when I said to you before, in our lithium metal system with Valence, we started with a lithium metal anode and a V6013 cathode. All the lithium that you need for the cell is in the lithium metal anode. In a lithium ion cell, imagine graphite when you start, and then you've got something like lithium cobalt oxide as the cathode. So it's in an uncharged state. And when you charge the cell, lithium then transfers from the cathode to the graphite electrode to charge the cell.
Yeah.
But you've got no metallic lithium in the system. Once you've got away from metallic lithium, suddenly there's not any mossy lithium growth, there's no dendritic lithium growth. So the whole safety abuse problem kind of largely went away. I'm not saying lithium ion cells are completely safe.
Yeah.
Not that we know there are some incidents, but they're significantly safer than anything you'd ever do with a lithium metal anode and a liquid electrolyte. Because
you still get with lithium ion, you can still have some issues with dendrite growth,
right.
and stuff like that.
There is a problem there, and that you hear a lot these days about developing cells with fast charge acceptance. Very important for electric vehicle applications, right, Ryan? Where you want to charge your lithium ion battery in 10 minutes, let's say, right?
Yeah.
If the rate at which you charge, there's a kinetic hindrance there, right? If you go too fast, then you don't do the insertion reaction into the graphite. So insertion between the layers of the graphite, it goes so quick that you get an accumulation of lithium ions at the surface, and that will cause a localized nucleation of plating and then dendritic growth.
Yeah.
So there's the problem. There's a real kind of issue for people developing fast charge acceptance cells, and that you have to really work on the kinetic issues around the anode electrode.
Yeah.
To overcome this problem of potential plating of lithium. And everyone kind of understands that problem, and there are ways of mitigating it. But like always in battery technology, you rarely get something for nothing, right? You have to offset something else, and that generally is energy density.
Yeah.
You have to make it in a slightly different way, more porous electrodes, thinner electrodes, this kind of thing, different electrolytes, and that generally causes a decrease in energy density.
Yeah. Yeah. And everyone's trying to rush to better energy densities typically, so there's always a bit of a tug of war there in terms of what the key priorities are. Yeah.
You're always, there's a thing called the Ragone analysis, right, as well, that you're probably aware of, where it's the relationship between power density and energy density.
Yeah.
Everyone's looking for good energy density and good power density, but you trade one for the other generally, and everyone kind of understands that.
Yeah. Yeah. This is at a simplistic sort of practical level. You've seen, or we've seen in the last few years, this sort of big, almost like a separation out of energy focused research and energy technology. So more and more energy density in cells, and then power focused, and
that's it.
You basically, the acceptance is you can't really have one without.
No.
Well, you can't have one and the other. You've got to sort of make a choice and go one way or the other.
That's always the problem. And like all companies, even like Faradion, right, our sodium ion company, we spend maybe 80% of our time trying to develop batteries for energy applications, just because energy applications are the majority, maybe 80% of them is of the market, perhaps, right? So we spend so much time on it, and we maybe spend 20% looking at cells for power applications. Yeah. But having said all that, power applications are growing fast, and we kind of at Faradion we split those into two different types of power applications. One where you need fast discharge rates, it's your kind of power tool application, things like that, where you're discharging the cell maybe in 15, 20 minutes.
Yeah.
But we also understand that that's okay, but you really need to understand the fast charge acceptance capability of the cell as well. Because if you're a power tool guy, right, you're using it for 20 minutes, but you want to be able to charge it back up in 10, 15 minutes. Yeah. And it's the same really for I'm sure you're aware, right, for EV applications. You really want to be developing maybe smaller batteries that you can charge up in 10, 15 minutes.
Yeah, it's that.
Do that. Because, the idea that the way Tesla have gone, and most of the electric vehicle companies, is say, look, all this idea about range anxiety means you have to go to larger and larger batteries, right? 60, 80 kilowatt hour batteries, which is fine, right? So you got 300, 400 mile range. But I think, there's obviously a cost consideration that goes with that, and also a safety. Big batteries are more unsafe than small batteries. So I think there's a big push in the market for the development of smaller batteries that you can charge very quickly. So cost advantage is much safer. Just have to have the infrastructure to go with it. But if you can rock up to a service station and charge your battery in 10, 15 minutes, I think that's kind of maybe acceptable, because most journeys aren't that long, right? But if you need to go on a long journey, if you can charge your electric vehicle battery in 10 to 15 minutes, hey, it's a cup of coffee, right? I think people maybe would accept that.
Used to be called the muffin stop.
That's it. Yeah. So I think it's the way to go, though. I think that's a good way to go. And I think we all thought you had to go to bigger and bigger batteries, right? It was Elon Musk's way of going, right? If you want large range, you don't want 40 kilowatt hour, you need 60 or 80 kilowatt hour battery. But I kind of think that's not the way to go. It's a big cost. We all know the cost of the batteries. We know as you get bigger batteries are more of a safety hazard. Got to consider that. So smaller batteries that you can charge up very quickly, I think, is maybe the way that a lot of the market's going to go.
Yeah. So to get back onto line here, because we've probably sort of jumped into now Faradion territory, but
maybe I should jump to that. Yeah.
Well, yeah. So Valence has kind of come and gone, and
But
then
Valence, before I leave Valence 1 second, Ryan, why I got into sodium ion was Valence gave me the task of being, I was the research director for Valence, so I did all their materials research.
right, right,
So Valence, for people who don't know, were the first company in the world to commercialize lithium iron phosphate batteries, right?
okay,
So we did that in 2002, and that was based on a material that I developed and a material that was made by our proprietary way of making lithium iron phosphate, low cost lithium iron phosphate. But it was funny, right? At that time, we were looking at a whole massive range of active materials for lithium ion.
yeah,
And when you start doing that kind of synthesis approach, we made hundreds and thousands of materials, screening them for their properties in lithium ion batteries. I was making sodium ion materials at the same time.
yeah,
And around about that same time, 2002, 2003, it was a real kind of back of the fume hoods Friday afternoon kind of deal. We made some sodium ion batteries.
yeah,
Just put them together, and we found there was absolutely no fundamental reason, no basic reason why sodium ion batteries wouldn't work in a very similar way to lithium ion batteries.
okay,
So we patented some of that, and we published on it as well at the same time.
yeah,
Kind of left it out there, and it was basically the first publication that really showed that you could put all the kind of components together and make something that clearly was maybe commercially relevant, because the numbers, you can run the numbers and the models for the system and the energy densities and all these kind of good things, and you could kind of see that this would be comparable with lithium ion.
yeah, yeah,
But I always say this to people, one of my biggest regrets was I failed to convince Valence that this was something worth pursuing. Valence, at that time, were just completely focused on making a business out of lithium iron phosphate.
yeah,
And I can support that. I understand that, right? It was struggling at that time. It needed to have a winner. So it decided
yeah,
to put all the sodium work to one side.
yeah,
But I kind of logged it away and said, well, clearly there was no fundamental reason why sodium ion battery technology wouldn't be commercially viable.
yeah,
I just logged that away. I kind of knew that. I put it in the back of my mind. One or two other people obviously knew that as well, and but I couldn't convince Valence, right? So that was a regret of mine, because they would have had a 10-year head start on everybody else. No one was working on sodium ion, right? Zero.
yeah, yeah,
I even say I say that to the guys who were, Valence has now kind of changed into lithium works now, if you know anything about the industry. And I still talk to the guys there on a regular basis, and we kind of laugh about it a bit. But there was I think, a missed opportunity, and I blame myself for not convincing the management at the time that was potentially viable. So I kind of logged it away, right? I put it in the back of my mind, that concept.
difficult times though back then. I mean, you probably were like 2000, 2002, 2003.
Yeah.
So pre-Dieselgate, pre. Elon Musk was still fiddling around with PayPal at that point, and hadn't thought about making electric cars yet.
Yeah.
So let's say I was going to say gold rush, but that is so not the right words to use. But the rush of activity and sort of and research effort that's gone on and investment in the last few years. Yeah, I mean, it wasn't back then trying to get anyone really to understand or invest in battery technology, because it was people were looking at in industrial applications or power tools or those were the kind of established markets.
It was.
EVs weren't even really on people's radars yet. So
No.
you can see every company like Valence sort of start a business, I guess, but not quite, but you know what I mean. That sort of young business, you've got to kind of focus on something, haven't you? You
do. And maybe Ryan, maybe they were right, because they made a business out of lithium iron phosphate, and it was strange. When we developed the lithium iron phosphate technology with Valence, I had a hard job, or we had a hard job as a team, convincing Valence that even lithium iron phosphate would be viable.
Yeah.
Because everyone understood, right, that this was maybe a 30% decrease in energy density over existing lithium cobalt oxide technology.
Yeah.
You'll say, well, why bother, right? It's an interesting technology, but why bother? It's not going to be competitive. What they hadn't realized that lithium iron phosphate is one, clearly much cheaper than lithium cobalt oxide, right?
Yeah.
Secondly, it had much better power capability for similar sized cells, and its cycle life was just outstanding.
Yeah.
Well, and the safety was better, right?
Yeah. Yeah.
When you put those things together, people in the market became more sophisticated. They understood that you don't get, as we said earlier, something for nothing. So they could dispense for a lot of applications energy density for these other attributes.
Yeah.
And you look at lithium iron phosphate now, right? It's still maybe 30% of the lithium ion market, maybe more.
Yeah.
Still maybe going up, right? So,
yeah.
and the performance now, it staggers me, Ryan, to be honest, right? When we first started working at Valence on lithium iron phosphate, we were making 18650 cells. That was the first product, right?
Yeah.
We were so happy when we produced the first commercial cells in China, and they were 100 watt-hour per kilogram specific energy. Right? We were so pleased with that as a performance. Right?
Wow. Okay.
So at that stage, lithium cobalt oxide was maybe 130 watt-hour per kilogram, in the same size, right? Because all size is important.
Yeah.
And now I see 100 Chinese manufacturers of lithium iron phosphate. Tier 1, Tier 2, Tier 3. I see them all the time, and you got stuff from BYD and CATL now, lithium iron phosphate. Okay, they're large format cells, but they're 180 watt hours per kilogram.
Yeah, yeah.
Fantastic, Ryan. What amazing achievement is that? That's almost doubled the specific energy.
Yeah.
Okay, the size is different, but I never thought that would happen. I thought you'd max out at a pretty kind of modest figure.
Yeah.
But people have done a fantastic engineering job on it. You have to say hats off, right? What an achievement.
Well, and just if we could, we're here, so we'll ask you, what is it that you think has delivered that? What's happened to make that possible that you didn't see was possible back then?
I think everything's improved, right? The aerial capacity of the electrodes is much higher, right? Much thicker electrodes, right? So you end up maximizing the active part and minimizing the inactive part of the battery. So you're minimizing current collectors, separators, electrolyte, stuff like that. And then everything else is improved. The graphite is improved a bit. The performance of the lithium iron phosphate, when we started, it was maybe running at something like 80% of the theoretical. Now it's at 100% now.
Yeah.
And you can buy this stuff for, you can buy good quality lithium iron phosphate powder at manufacturing quantities at less than $10 a kilogram in China. Fantastic.
Yeah.
This is, all these things have kind of come together. But it's not mainly been around engineering improvements, not chemistry improvements.
Right. Okay.
Just packing it better, making the electrode better, increasing the active loadings, all those good things. But I seriously didn't imagine that it would go from 100 to 180. No way.
Yeah. And what do you think of sort of the cobalt-based stuff that's kicking around at the moment?
Cobalt, you mean as in NMC and stuff like that?
Yeah, the different those different technologies.
Yeah. So obviously, lithium cobalt oxide was at the time when lithium iron phosphate came along. That was the incumbent technology. There's still a bit of that around, but not much. So everything now is around either NCA, nickel, cobalt, aluminium.
Yeah.
I hesitate aluminium. I can't even say aluminum because I've kind of been like romantic. I don't know who I'm talking to. I keep on moving back and forth. So nickel, cobalt, aluminium. I'll say it in the Europe.
Yeah.
And then NMC, nickel, manganese, cobalt. But nickel, manganese, cobalt, great technology. But people are trying to go to high nickel, low cobalt for obvious reasons, right?
Yeah.
So now the ultimate, as you're probably aware, Ryan, that the ultimate in NMC right now is a thing called 811.
Yeah.
So 80% nickel, 10% cobalt, 10% manganese. It's a great material, but it has some it has some issues as well, right? It's a tough material to handle and deal with, and safety and things like that. So trying to minimize the amount of cobalt in the formulation is good. And that maybe that's a good segue into sodium ion, Ryan, because so I say right back, got back to back in the UK at this stage later on after I'd left Valence, and there came an opportunity with two other people actually. Someone who was running a VC company and a colleague of mine, Chris Wright. We were asked to kind of put together maybe some ideas around startup companies in energy storage.
Yeah.
And that's what was the precursor to making Faradion. I said, look, something that I know will work and hasn't been tapped into quite yet is sodium ion technology.
Yeah.
So we got some initial seed funding in 2011 and established Faradion as 100% looking at sodium ion technology, right? We were the first company who can look at sodium ion.
Yeah.
And, why we were interested, right, was clearly we'd shown previously that this stuff worked. Secondly, that we could probably make the cathode chemistry that would be low cost, no cobalt kind of formulations for the cathode.
Yeah.
And most importantly, Ryan, that you could make all this stuff on existing lithium ion manufacturing lines.
Right.
There's so many startup companies out there that have come up with some pretty interesting cell chemistries and then said, well, this is great, but by the way, you need a new manufacturing method in which to scale it up.
Yeah.
Several out there. We could go through those on another call sometime. So we decided that it was very important, if you're going to try and license this technology or get this company established in the market, if you could say to an existing lithium ion manufacturer who'd invested in their manufacturing lines, look, sodium ion technology has some big advantages, and guess what? You can run it on your existing infrastructure, same cell formats and everything. This would be a big selling point.
Yeah.
And that's what's proven, right? That's exactly what's proven out. Our manufacturing partners now, that one or two of them are in China. We've got one in the UK. They literally are lithium ion manufacturers. They just run our sodium ion chemistry on the same lines, no difference.
Yeah.
So that is a major selling point for the technology.
I guess they have to sort of just shut the line down and clean it out, and then put the new.
Exactly.
Right.
Exactly. There's one of our Chinese manufacturing partners. Seriously, Ryan, it sounds simplistic, but this is absolutely true. They run lithium ion on their manufacturing line for 4 days of the week, and they transfer to sodium ion on the 5th. It's that simple. Right. The only difference, we always said when we were talking to our investors at the start, we said, look, what we're going to do for you is we're going to rock up to the boardroom, show you two cells, right? One will be lithium ion, one will be sodium ion, and the only difference you were going to tell, if you don't do any chemical analysis of this thing, is that the lithium ion cell has one current collector is aluminium, one that's copper. For sodium ion, it will be exactly the same, but both current collectors are aluminium. That's the only difference.
Right.
So we said if we could do that, more sustainable, lower cost, better safety, there's got to be a market for it. And that's kind of currently where we're at. I think everyone now has decided that there's a market for sodium ion. It's now trying to figure out whether it's 1% of the market or 25% of the market. We're not quite sure, to be honest.
And what sort of applications are you finding that sodium ion really has an advantage in? Where are the sweet spots for it?
Well, initially, right, where we're getting, this is the market pool now, right? So obviously we talked to a lot of people who are out there asking for us to fulfill applications. So initially it's around large format stationary. So we're starting, right, but that's only a start point. So stationary, battery backup, telecoms backup, UPS, some renewables actually as well, PV backup. So things like that. But, we're at the early stage of what we can achieve in terms of energy densities and power densities. So we're not ruling out the possibility that we can move into automotive going forward.
Right.
We're also, because our power density is pretty good, we're already looking at things like lead acid replacement for things like SLI batteries, starting, lighting, ignition.
Okay.
I think that's a very big market.
Yeah.
It's not currently being tapped by lithium ion because of the things like the cost.
Yeah. Well, the lead acid batteries market's huge still.
50%, 50% of the rechargeables market by value is still lead acid. Obviously, it's lead acid's going up at more kind of organic growth, and lithium ion's going up at 20% a year or whatever.
Yeah.
It's still right now it's close to 50% of the rechargeable market is lead acid.
Oh, that's interesting because I've seen people starting to look at things like so the forklift truck market, for example, and replacing lead acids with lithium.
That's it.
But it can sometimes it works, but sometimes it doesn't work commercially. So I guess you're that kind of thing. You'd be better positioned to do potentially.
Lovely. We've talked to. It's strange. This is a strange one, right? Sometimes some applications kind of just blow your mind, really. But forklift truck applications, we talked to several forklift truck companies, and what they like about lead acid is not just because it's the incumbent technology, but it adds ballast to the forklift.
Yeah, it's heavy. Yeah.
So here's your problem, right? You come on with something that's 5 times the energy density in terms of watt-hours per kilogram. And they say, yeah, but we're going to have to add weight to the back of the forklift if you go that way. We like the fact that it's a fifth of the size and a fifth of the weight. But we don't like the fact that we need to have ballast on the back of the forklift.
Yeah.
So there is a market there, but you have to kind of think it through a bit. It's a kind of weird one, that. We have looked at that, by the way. But I'll give you some ideas, though, Ryan, about where we are in terms of... Because the big driver for automotive really comes down to, I'm going to slightly contradict what I said earlier about fast charge acceptance, but it generally comes down to energy density, right? It's got to be high energy density to really get into automotive EV. You can't go along with a technology that's 100 watt-hours per kilogram when NMC is up at 240.
Yeah.
It's a tough one, right? Or NCA is much the same, right? 220 to 240. It's a tough one. So where we are currently is our cells that we make with our manufacturing partners are about 150 to 160 watt-hours per kilogram.
Okay.
So it's pretty good. So it's comparable with like LFP for lithium iron phosphate.
Yeah.
But we are real early door. This is really early times. Our roadmap, and this is an engineering roadmap more than a chemistry roadmap, is that we think we can get to 190 in 6 to 9 months from now.
Okay.
Well, if we start talking seriously, people have kind of discarded maybe sodium ion for high energy density applications like automotive.
Yeah.
But if we can get into the numbers that aren't far short of NMC, there is no reason why we can't penetrate that market as well. We don't think so.
We've still got, you do have, LFP is being used still. Even, what Tesla's starting to put LFP in cars in China for that market, and the transit bus market, LFP is still very popular there.
That's it.
Because
actually, we are looking at that bigger market. A couple of things that Faradion have announced is one is putting it into trucks.
Right.
Very large trucks, and you're right. Things like buses are a big one for us as well, potentially.
Because the other big driver, you've got energy density is important. Watt-hours per kilogram. Volumetric energy density is important as well.
Absolutely.
How do you measure up on volumetric?
Volumetric, we're in the same range as lithium iron phosphate.
Okay. All right.
So generally, because the formats are very similar, people walk around with these rules of thumb, right, where they say if you give them a watt-hour per kilogram figure, generally people say, well, they'll kind of guess that the watt-hours per liter is generally something like somewhere between 1.5 and twice the watt-hour per kilogram figure. Yeah. So our 150 to 160, big surprise, comes out to be somewhere kind of 280 watt-hours per liter.
Okay.
Like that. That's the same as LFP. Basically.
Yeah.
It's not bad. You know,
Yeah.
you see some of these numbers right now that are banded around with like the NMC 811 with silicon doped graphite systems, right?
Yeah.
That's the ultimate anode system. You get some real kind of wacky numbers where the watt hours per liter are up at 750 or
Yeah. Say
something.
700, 800. Yeah. Yeah.
Kind of blows your mind.
Yeah.
We will never get to that figure,
Yeah.
but that market where LFP is, we think we can move into that and beyond.
Yeah.
So it's pretty reasonable actually.
Because the other big driver, so we've talked about energy density, volumetric energy density, but the third, I don't know, these would probably shuffle around in priority, but cost,
Yeah,
the C
yeah, yeah,
word,
yeah. Cost.
cost.
So
So
important.
how does that kind of look? Is that the big advantage for sodium ion over lithium ion?
It is. It is. So we you know when we started this whole thing, Ryan, we you know when we used to go out and give investment calls or go to see companies with looking for new applications and things like that, we always used to go in and say, look, we're clearly zero lithium, right? We're a sodium ion company, and we're zero copper as well. We don't used to use copper
Yeah.
in the system either. But now we quite often say the first thing we say is we're zero cobalt, right?
Yeah. Yeah.
Because everyone knows about what's going on in DRC and all the rest of it. So people get that, they totally get it. So now we're saying we're zero cobalt, we're zero lithium, and we're zero copper.
Yeah.
So what we do is we're constantly looking at our costs in terms of the bill of materials, so what all the bits that go in to make the cell, and we compare ourselves with LFP and NMC lithium ion at a similar manufacturing scale, because obviously there's a volume to this.
Yeah. Yeah.
And we will always be cheaper than LFP and NMC in terms of dollars per kilowatt hour for an energy application.
And are we talking like a couple of percent, or are we talking
30,
like
30, we think. 30 is what we normally say.
30%?
Yeah, so it's significant, right?
Yeah. Yeah.
And why we say that, right? You say, well, that's an easy figure to say, but we the supply chain is already there, right? Because one of the other advantages of being able to make our cells on a lithium-ion manufacturing line is we can use the same supply chain for a lot of the common elements. So It's not like we've got to go out and rebuild a new system for a new components. They're the same components. And our cathode material is much more efficient. Now, I said to you earlier about things like NMC 811. So 80% nickel, right? 10% cobalt, 10% manganese. Ours is a nickel-based cathode material, but it's more like 30% nickel. Right. It's a much more cost-efficient solution.
Okay.
So we kind of feel at a similar manufacturing scale, we will always be cheaper than lithium ion. Hey Ryan, what's not to like, Ryan? What's not to like, right?
Well, yeah, exactly. I mean, you can. There's lots of applications today where actually energy density don't matter at all. So we talked about some where, it's less important, but in, grid storage, for example, or backup battery systems, UPSs, emergency lighting, and you can just rattle off a whole list of industrial applications where it doesn't really matter. You're either competing against, lead acid or against nothing. So things like grid stabilization. That's just a new market altogether. So
behind the meter applications is very big.
Yeah,
we see that. You're absolutely right, Ryan, what you're saying, because we originally thought back in 2011, maybe naively, that we had to be a lithium ion beta. We had to do something better than lithium ion, which we still give ourselves that as a target, right?
Yeah.
You probably guess from the numbers I've been saying, comparing ourselves with LFP and NMC. But the reality is that we can be a replacement for lead acid in a lot of applications. A lot of people don't like lead acid. It's been around a long time.
Yeah.
A lot of people like it for maintenance and lead and how heavy it is and all the rest of it. So there are a lot of applications where we don't have to be a lithium ion beta. We just have to be better than lead acid.
And just for me, so lead acid, right, is well understood. It's kind of big chunky batteries, pretty simple stuff, but they do they degrade over time, so you've got to have to replace them, as everyone will know. Flat battery on your car, new replacement starting battery on your car, but all of the sort of stationary applications like UPSs and safety lighting, stuff like that. What that then means is there's a maintenance cost that you have to go around and replace the batteries periodically, which requires people and spare parts. And the other big thing with lead acid that people don't like, so as well as sort of relatively slow recharging and such, but there's a big problem with off gassing when they're being charged. So they produce hydrogen gas.
Yeah.
If you're cycling them really hard, actually they effectively consume the fluids in them as well. So you kind of have to keep topping them up and adding fluids and stuff. So how does so this is probably, and don't, well, you can laugh at me actually if you want. It's a stupid question, but how does sodium ion compare against all of those things with the lead acid? How long is it going to last? Life cycle rating. Presumably, there's no sort of
good question.
Any maintenance needs, or does it just
no maintenance? Same as lithium ion.
Yeah.
Cycle life, that's improving all the time. Cycle life is probably the most difficult thing to quantify because it's tested in so many different ways, right? The rate, the depth of discharge, the temperature, all these things. But we are now rating our cells at something like 3,000 cycles when we charge and discharge them to 80%, which is kind of typical.
Yeah.
It's pretty good. It's like lithium ion. We're not saying we're better than lithium iron phosphate. We're clearly not at this stage.
Yeah.
But we're in the same range. So it's maintenance free. It is good cycle life, and 5 times the energy density of lead acid.
Yeah.
So to me, it looks pretty good, right? It can't do all applications, but it's good for a lot. It really is.
Yeah, and that cost advantage. How does it perform with temperature? So one of the other challenges with the lithium ion and lead acid, but for slightly different reasons, is they don't like being cold or hot, but particularly cold. So it's quite hard to charge lithium batteries as they get colder. So what that means is you then have to heat them, typically, if you're operating them in an environment where they're going to be cold, which when you start to think about these things is a lot of, there's a lot of environments that actually are cold. How does sodium ion look in that respect?
We actually hold that up as an advantage over lithium ion, actually, Ryan. So that's a good question. Lithium ion, it depends again on a lot of the problems with temperature come down to the properties of the electrolyte in lithium ion. And generally speaking, there's not that many different types of electrolyte. There's variations on the theme, but you're probably aware, right, that lithium ion operating range is generally at best minus 20 C to plus 60. That's about what it can do.
Oh, and that would be really at that would be really at best getting the
minus 20. So that's at best. You're probably right. That's at best.
There's a few cell suppliers just had heart attacks and fallen over there. You're going to charge my cells at minus 20.
Well, the problem is actually that temperature. Unless you do something about the electrolyte, it freezes out. There's a component in the electrolyte called ethylene carbonate that you kind of have to use.
Yeah. Without
going into all the chemistry, you kind of got to use that component, that solvent in the electrolyte, to be compatible with the graphite anode.
Right.
There's good reasons why you have to do that. People would like to use a solvent called propylene carbonate, and propylene carbonate only differs from ethylene carbonate with an additional CH3 unit on the ring. It's very similar material. But you can't use propylene carbonate with graphite. Right?
Yeah.
Well, no, impossible, cannot be done. We don't use graphite. We use an anode called hard carbon, which is a disordered version of carbon. It's not like graphite; it's all nicely layered.
Yeah,
it's a disordered carbon. And one of the advantages of using hard carbon is you can use propylene carbonate, and that has a much better liquid range than ethylene carbonate. So we have, at the bottom end, we can generally take our cells down to negative 30 degrees C.
Wow.
and take it up to at least plus 60 on the high side. So we have a bit of an advantage over lithium ion in this range. That is why, Ryan, I know when we first started this talk, you were asking me about applications, and I said SLI was something we were kind of looking at, starting lytic ignition.
Yeah.
That's one of the real reasons why lithium ion hasn't really penetrated that market particularly well, because it's terrible at low temperature, right, generally. So that cold cranking test...
Minus 40 cold cranking.
And excursions to plus 80, right? They ask for excursions to plus 80. If you leave it on the dash in Phoenix in the sun, it gets up to more than 60 degrees C.
Yeah.
So ours does a lot better than that at low end and high end. So temperature range is one of our advantages, and it really comes down to the fact that we have more latitude in the electrolyte combination.
Wow. Okay. Interesting.
Yeah, it's not bad.
Yeah. So then, just kind of mindful of the time actually now, because we've it's flown by.
I told you I could talk a bit about this stuff.
Well, I tell you what's absolutely fascinating, and I guess people listening will clearly be able to see that what you don't know about batteries of all types probably is not really worth knowing actually. So it's been
very nerdy.
Fascinating. So in terms of the future, then, what does the future hold for you guys? What's next for Faradion?
Yeah, our next steps are getting this into applications. We've announced a few press releases of things where we're going to do demonstrations. That's in Australia and in India, and now we are basically, Ryan, dealing with huge numbers of expressions of interest in our technology.
Okay.
So we've got to take it now. We've maybe made with our manufacturing partners in China and in the UK, we've probably made, I don't know, a couple of 100 kilowatt hours of production. It's not a huge amount, right? In standard formats, in cylindrical, in pouch cells and prismatic, just to show that everyone this is capable of any format, we've now got to take it to the next level. So we're looking at partnerships that allow us to scale up our technology and at the same time fulfilling all these requirements for applications.
Yeah.
And also we will be looking to license the technology to existing lithium ion manufacturers.
Okay.
And there's a lot of interest. We have, I would say, maybe calls on this, certainly weekly, people expressing an interest.
Okay.
So what we need to do is get to that next step.
Yeah, I was wondering on that one of the other challenges in the market right now is capacity, and I mean capacity in terms of there's I don't know, half a dozen big lithium ion cell manufacturers, and basically if you're not, particularly in the automotive world, if you're not committing to multiple gigawatt hours a year of requirements, they're not interested in talking to you. So I know that for applications off to one side in adjacent markets like power tool, we talked about that was an early one, but current power tool market, robotics market, grid, etc. A lot of these markets they just can't get cells, and even actually, I mean, Tesla themselves talk about they slowed down the development of some of their new products because they just couldn't make cells fast enough for the automotive part of the business. So, what is that a challenge for you guys, or is that an opportunity? So, in terms of getting the attention of cell manufacturers, are you sort of appealing to people who aren't in that kind of tier one crop to give them some big difference?
Brian, actually, it's a good question. That's a really good question. If you're trying to make some kind of beachhead, get into the market, what do you do as a strategy? Do you go to the tier ones?
Yeah.
Go to the Samsungs, the LGs, the CATLs, or do you look at companies that may have some may have some excess capacity that they can use, right? Tier twos, tier threes.
Yeah.
We've taken the initial view that it's maybe better to go to tier two and try and get into the market that way.
Yeah.
But we're talking to the tier ones as well. We absolutely are. And I tell you what, Ryan, as well, when we first started on this kind of exercise of Faradion and sodium ion, when we talked to the tier ones, maybe 5, 6 years ago, we had to do a lot of convincing that sodium ion was part of the future, right? We really had to do a very good selling job
Yeah.
on these companies. Well, why sodium ion? We got this great lithium ion technology. Seriously, Ryan, it's an open door now.
Yeah.
They're all working in this space. Every company, we're pretty sure that every tier one company has a group now working on sodium ion.
Wow.
So we think as Faradion in the UK, we've got the best IP portfolio by a distance, right? We're the early company.
Yeah.
There's maybe 5 or 6 other sodium ion companies worldwide now, but they're all playing catch up. So we've just got to use that advantage of being the earliest company into the market.
Yeah.
So I think that's good, but it just keeps the pressure on us all the time. It's a tough spot.
Yeah.
People are there. We got, as I say, maybe five other startup companies plus all the big lithium ion makers in the same place.
That's a challenge at the moment as well. With we certainly see that as a business where you kind of. We've been in the EV space for a long time, not as long as you've been in batteries, but 15 years in electrification, and there's a lot of investment, a lot of R&D dollars going into the market now, and actually that early maintaining that kind of lead is tough. Trying to keep in a position where actually the big guys were sort of. It is ironic that 3-4 years ago some of the tier ones like laughing you out of the room for talking about electrification, or in your case, sodium ion, but now chucking millions, if not billions, of dollars at it.
They are. But lithium ion, you can talk to anybody, right? If I were to call out, it's still, although we say it's a massive market now, the lithium ion, all the rest of it, it's still kind of a market where you can talk, all the big players in the market, you can talk to these people fairly easily, right? We know the people in the tier ones, the tier twos, tier threes. You can talk to anybody now about sodium ion and they get it. You don't need to convince them that this is part of the future.
Yeah.
So I think we've got a big opportunity, but as you quite rightly pointed out, that's no guarantee of success. We just got to keep focused and keep ahead.
Yeah, keep it moving. Okay. Well, yeah, brilliant. So if people are interested, what I'll do is in the show notes, I'll put some links there to Faradion and to Jerry's LinkedIn profile. So if people want to get in touch with him, they'll be able to find him that way. If you're interested in sodium ion batteries and you think it might be something that's good for an application that you're working on, it'd be easier to get in touch with him that way. We'll put some other show notes down there, but that is all we've got time for today. So thanks Jerry for taking the time out to join me. Thank you to everyone for listening and for taking the time out to listen to the show today. I've learned loads from that. I hope you've got something out of that. Don't forget to like us or leave us a rating and a comment or review, depending on which platform you're listening to us on. We are available on every major podcast platform now. I think some people are finding us through YouTube, but then going across to Spotify or Apple for their kind of regular dose. So don't forget to subscribe to find out what we are doing. And remember, if you've got a question on anything to do with the electrification or autonomous market, do shoot them in, and we might be able to turn that into an episode. And if you're doing something really interesting and cool in the EV space or the autonomous space, do get in touch as well. We'd love to hear from you. Be great to have you as a guest on the show. So like I said, that's all we've got time for, and I really look forward to speaking to you again soon.